Okay, welcome everybody to the Virtual Time Series seminar. It's my great pleasure today to introduce our speaker, Stefán Guðmundsson from Aarhus. He's joined by Bjarni Einarsson from the Central Bank of Iceland. And the topic is detecting giver and receiver spillover groups in large vector autoregressions. So Stefán, thank you so much for joining us, and the floor is yours.
Thank you for having me, and of course, thank you to the organizers. Now, as Majid said, I'm going to talk about finding spillover groups in vector autoregressions. Now, recently, the latent group detection problem has become quite popular in time series econometrics. In a nutshell, this problem consists in partitioning the series of a time series panel into groups based on similarity. And how we measure the similarity, of course, depends on the application at hand. Now, this literature has approached the problem from a variety of different angles. For example, using Bayesian Markov switching models, panel data models with unobserved effects, and block factor models. The methods in this literature have been used to study, for example, group structures in business cycle synchronicity, convergence clubs, and volatility spillovers. Now, in a series of papers, we take a slightly different approach where we find groups based on detecting blocks in various matrices. First, for the sample covariance matrix, then in a follow-up in the autoregressive matrix of a vector autoregression, and then in this paper, again in the autoregressive matrix, but this time we find groups based on giver spillover behavior on the one hand, and then groups based on receiver spillover behavior on the other hand. And then Majid and I are also working on another paper in the series where we do something similar with non-stationary data. Now, all of these methods are spectral and use the singular value decomposition, and they're inspired by the community detection literature, where community detection is a classic group finding problem in the networks literature. Now, the goal of the paper is to partition a panel of time series into groups based on its spillover structure. So let's consider a first-order vector autoregression, where I focus on a first-order VER for simplicity. The autoregressive matrix phi here summarizes the spillover dependent structure of the VER, so that the ith column is the spillover effects that variable I gives to others, and the ith row is the spillover effects that variable I receives from others. Now let phi hat be the OLS estimate of the autoregressive matrix. We wish to group the series based on this matrix. I introduce an algorithm that groups the series based on their giver spillover behavior, that is using the information in the rows of the matrix, and then separately groups the same series into groups based on receiver spillover behavior, that is using the rows in the matrix. I call the algorithm the directed spillover community finder, or DISCO finder for short. The algorithm uses the singular vectors of the sample autoregressive matrix to find the groups, and it's useful for finding groups of series that exhibit similar giver spillover behavior on the one hand, and groups of series that have similar receiver spillover effects on the other hand. In addition, the algorithm is simple to implement in just a few lines of code and comes with large sample performance guarantees. Now, let me show you an illustration. Here we have a heat map of the sample autoregressive matrix corresponding to a panel of volatility measures for the members of the S&P 100. As you can see, there is evidence of a group structure in the columns, but not so much in the rows. So I run the algorithm and ask it to find two groups in the columns and nothing in the rows, and then order the series by the groups that it finds. And as you can see, it recovers a strong giver spillover group structure over the columns. Now, this is not the first attempt to find spillover groups based on vector autoregressions. Chen, Herdl, and Klochkov have a model where series in the same group have equal rows in the autoregressive matrix. And Chu and Pan have a model where where series in the same group have equal row sums in the autoregressive matrix, and then they estimate the group membership based on these models. But these models are a little bit restrictive, and they only find groups based on the row behavior, that is, the receiver behavior. Now, as I mentioned earlier, we also had a paper where we looked for spillover groups in VERs, where we proposed the VER blockbuster algorithm. Now, loosely speaking, what this algorithm tries to do is to order the sample autoregressive matrix so that it has strong diagonal blocks and weak off-diagonal blocks. That is, groups such that the spillover effects are stronger within the groups than between them. And here you can see an idealized example of such a group structure. Now, if we go back to the volatility panel for the S&P 100 and run the VER blockbuster here and ask it to find two groups and then order the series by these groups, as you can see, the results are not particularly impressive. And the reason is that the VER blockbuster is designed for symmetric spillover structures. And thus, it cannot distinguish between the giver and the receiver behavior, and instead finds groups based on the average of the two. But as the example showed us, we cannot always expect symmetric spillover structures, and in this case, the VER blockbuster might not be the correct method to use. On the other hand, the disco finder is designed for asymmetric spillover structures and can find symmetric structures as a special case. The highlight of the algorithm is that it can detect both the giver and the receiver spillover group structures, and to the best of my knowledge, it's the first algorithm that can do both. Now, the plan for the talk, I'm going to begin by introducing the algorithm, and then I'm going to establish performance guarantees for this algorithm. To this end, I introduce a flexible network-based VER model with an unknown group structure, and then show that the algorithm consistently recovers this unknown group structure when the number of series and the number of observations are large. Finally, I use the method to study group structure in the volatility spillovers amongst the constituents of the S&P 100. Now, suppose we have P observations on n time series. The goal is twofold. We want to partition the series into kg giver groups such that series in the same group have similar spillover effects that they give to others. And then we want to separately group the same series into kr receiver groups such that the strength of the spillover effects that they receive from others is similar. I assume that the numbers of groups, kg and kr, are known. And the disco finder algorithm goes as follows. We begin by calculating the sample autoregressive matrix using OLS. Then we let k be the smaller of the group numbers, so the smaller of kg and kr. And we take the right singular vectors corresponding to the k largest singular values of the sample autoregressive matrix, and we arrange them into the n by k matrix U hat G. So there are n rows and k columns, one for each of the singular vectors we took. Next, we row normalize this matrix so that each of its rows has length 1. And we call the result the row normalized right singular vector matrix X hat G. We then do the same thing for the left singular vectors corresponding to the k largest singular values of the sample autoregressive matrix and call the row normalized matrix of these vectors X hat R. Finally, we apply the k-means clustering algorithm to the rows of the X hat G matrix to find the kg giver groups, and then we separately apply the k-means algorithm to the rows of X hat R to obtain the kr receiver groups. And it's worth mentioning here that the algorithm is also quite computationally light. Now, I'm going to establish performance guarantees for the algorithm within a class of VER models that I will now introduce. And in these VER models, the autoregressive dependence structure is determined by an unobserved random graph. There are thus two layers of randomness in this framework. First, the graph G is drawn from a random graph model. And then the data are drawn from a VER1, where the autoregressive matrix is a function of the graph. And in particular, I assume that the graph is drawn from the stochastic block model, which is a popular random graph model, which has a group structure. But before we discuss the model, we need to go through some preliminaries. Network analysis has also recently become popular in time series econometrics. Here, the focus is typically on learning the network dependence structure of a time series panel. To this end, we give the panel a network representation where the series of the panel are represented by the vertices of the network, and the dependence relations between the series are represented by the edges of the network. So we define a directed network or a directed graph G as the collection of two sets. The first set is the vertex set that contains the n vertices that represent our series. And then you have the edge set that contains the edges that represent the dependence relations between the series. When we're analyzing graphs, it's often helpful to use so-called graph matrices. The first one is the adjacency matrix A, which summarizes the edge structure of the graph. This is an n by n matrix where the ijth element is equal to 1 if there is an edge from vertex I to j in the graph and 0 otherwise. We then have the out degree matrix, which is a diagonal matrix with the out degrees on the diagonal. And the out degree of vertex I is defined as the number of edges that vertex I sends to others. We can analogously define the in degree matrix, where the in degree of vertex I is the number of edges that vertex I receives from others. And then we define the Laplacian matrix as a normalized form of the adjacency matrix, where we pre-multiply with the inverse root of the out degrees and post-multiply with the inverse root of the in degrees. Now, a random graph is a graph where the vertex set is fixed, but the edges are randomly and independently drawn based on Bernoulli triangles. So in a random graph, the vertex set is just like before, but there is an edge from vertex I to vertex j with probability Pij. And the simplest possible example of a random graph model is the Erdős-Rényi random graph, where Pij is equal to P for every pair ij. So the same edge probability for every possible pair of vertices. Another example is the stochastic block model that allows for group structures. In particular, the vertices are partitioned into kg giver groups, and then the same vertices are also partitioned into kr receiver groups. The edges are then randomly and independently drawn, and the probability of an edge from vertex I to vertex j is equal to pgr if vertex I belongs to giver group G and vertex j belongs to receiver group R. Now let's see a graphical illustration. Here we have a stochastic block model with 50 vertices, and we have two giver groups. And here we add the edges that are randomly drawn. But then we also have three receiver groups. So you see we have two separate group structures over the same objects, and we want to recover both of them. Now, to ensure that we can recover the group structures of the stochastic block model, we need to make some assumptions on the edge probabilities. Now, first, take the edge probabilities, the PGR probabilities, and arrange them into the Kg by Kr matrix B. I assume that this matrix B has full rank, and this just ensures that the groups can be separated from each other in population. Now, when characterizing the behavior of random graphs, when n, the number of vertices, gets large, it's natural to do that based on how the edge probabilities evolve as a function of n. Now, I assume that the edge probabilities cannot shrink to 0 at a rate faster than log n over n. So in other words, the edge probabilities are allowed to shrink, but they cannot shrink too fast. Now, loosely speaking, this is just ensuring that there is sufficient signal in the graph when n is large so that we can recover the group structure. Now, it's also worth mentioning here that this assumption is not specific to the algorithm that I'm proposing here. It can be shown that this regime here is the sparsest regime where you can hope to fully recover the group structure, which we want to be able to do. Now, we're now in a position to discuss the model. Consider a panel of n time series. I'm going to introduce a VER model where the autoregressive matrix is a function of the graph G, which is drawn from the stochastic block model. The graph is defined over n vertices, and each vertex represents a series in the panel. And the model is designed so that the jith element in the autoregressive matrix is non-zero if and only if there is an edge from vertex I to j in the graph. So there are thus two layers of randomness in the model. First, the graph G is drawn from the stochastic block model. And then the data are generated from a VER1, where the autoregressive matrix is a function of the graph G via the graph Laplacian. And here, this little phi there is just a positive constant. So the model consists of these three equations. First, the graph is drawn from the stochastic block model. This then determines the autoregressive matrix via the graph Laplacian, which in turn defines a VER1 whence the data are drawn. And a key feature of the model is that the autoregressive structure of the vector yt is determined by the graph G, in the sense that there is an edge from vertex I to j in the graph, if and only if series I Granger crosses series j in the panel. Now, you can show that the resulting VER is going to be covariant stationary if this coefficient phi is less than 1. And of course, in the presentation, I'm focusing on a simplified version of the model for ease of exposition. In the paper, I allow for some generalizations. For example, I allow for higher order VERs. One of the properties of the stochastic block model is that within a given group, all the vertices have the same expected degrees, which is restrictive. In the paper, I use an extension of the model that allows for general degree distributions, and in particular, power law. In the model, as I described it earlier, the adjacency matrix is a binary matrix, just zeros and ones, which of course leads to a restrictive structure in the model. But in the paper, I allow for weighted graphs where for each successful edge, we also draw a random weight, which just allows the model to be much more flexible. Now, as I mentioned earlier, I assume that the numbers of groups kg and kr are known. And of course, in practice, this is not always going to be the case. But I also suggest a likelihood-based criterion that can help us select these parameters in practice. Now, I'm going to spare you the full details of the theoretical analysis, but I want to show you or give you a quick overview of the proof strategy. Now, to keep things simple, I'm going to assume that the numbers of groups are equal in this section. And I'm only going to focus on the giver groups for ease of exposition, but identical results would hold for the receivers in this case. Now, the proof proceeds in 3 steps, and the first step is a population result. Now, let phi bar be the population autoregressive matrix, and define it analogously to the random graph autoregressive matrix we saw before, where we have replaced the adjacency and degree matrices with their expectations. Now, let the calligraphic XG be the row normalized matrix of the right singular vectors corresponding to the k largest singular values of the population autoregressive matrix. I'm going to call these the population singular vectors from now on. The first step of the proof shows that if k-means is given the population singular vectors, it can trivially recover the group structure. Now, recall the matrix X hat G that we had when we discussed the algorithm. These were the row normalized right singular vectors corresponding to the k largest singular values of the sample autoregressive matrix. I'm going to call these the sample singular vectors from now on. In the second step of the proof, we establish the concentration of the sample singular vectors around their population counterparts up to a rotation. Now, first notice that the sample autoregressive matrix differs from its population counterpart due to these 2 layers of randomness. So to bound the distance between the population and sample autoregressive matrices, we need to bound these 2 colored terms. Now, the first one, the red term, I call the random graph concentration term. This is the distance between the random graph autoregressive matrix and its population counterpart. To control this, I extend the classic random graph concentration results of Oliveira to allow for directed and weighted graphs. And then there is the second term, the orange one, which is the sampling variation term. This is the distance between the sample autoregressive matrix and the random graph autoregressive matrix. Now, to control this, I extend the concentration inequality from Roman Verschinnen. The original inequality assumed sub-Gaussianity and IID data, but using the Bernstein inequality of Merlevet, Pellegret, and Rio, we can relax this and allow for strongly mixing data with generalized exponential tails. I want to quickly show you the assumptions that this affords us for the data. First, YT needs to be strongly mixing, and the alpha mixing coefficients are decaying exponentially. Here, this parameter gamma 1 is governing the strength of the decay. So the larger gamma 1 is, the less dependence you have. And here is the generalized exponential tails assumption. So you can see here that gamma 2 controls the strength of the decay of the tails. So the larger gamma 2 is, the thinner the tails. And there are some interesting special cases here. For example, if gamma 2 is equal to 2, you have the sub-Gaussian family. If gamma 2 is equal to 1, you have the sub-exponential family, and so on. Now, finally, I summarize these 2 gamma coefficients into one that I just call gamma. So the smaller gamma is, the more dependence and the thicker the tails in the data. And this gamma coefficient will show up in the final result. Now, these assumptions are required to use the Bernstein inequality of Merlevet, Pellegret, and Rio. And as a consequence, they've become quite common in the time series literature recently. Now, at this point, we have controlled the spectral norm of the difference between the sample and population autoregressive matrices. So all we need to do is to translate this into a statement on the singular vectors. And this we can do with a modification of the Davis-Kahan-Vedden theorem due to O'Rourke-Owen 1. Now, for the final part, we can establish a condition that guarantees that a vertex is correctly grouped by k-means. And we can then define the set of incorrectly grouped vertices for as the vertices for which this condition is not satisfied. Then in the final step of the proof, we establish a theorem that says that the fraction of incorrectly grouped vertices is going to 0 when n and t get large. And here you can see the theorem. Now, M here is the set of incorrectly grouped vertices. So on the left-hand side here, we have the fraction of incorrectly grouped vertices. And this is upper bounded by these two terms with high probability when n is sufficiently large and t is sufficiently large relative to n. Now, the first term in the bound here comes from the random graph concentration, and it goes to 0 under our assumptions on the edge probabilities. The second term is coming from the sampling variation because we estimate by OLS here. And we can also see here that the condition on t depends on the gamma coefficient. So the smaller gamma is, the more dependence we have, and the thicker the tails, but at the same time, the more observations we require to consistently recover the groups. Now, in the paper, I also have some simulation studies just to verify that the algorithm works in finite samples. But I'm going to go to the application now, where I use the method to study group structure in the volatility spillovers amongst the members of the S&P 100. Now, the data set I have here has daily volatility measurements from the beginning of 2005 to the end of 21. And I only include companies that have been trading throughout the entire sample. So this gives us 84 companies and around 4,000 observations. Now, we had already seen the heat map of the sample autoregression matrix where the series were ordered alphabetically. And then we had also seen how it looks after ordering by the two giver groups that the algorithm finds. And here you can see a network plot of the results where you can see the tickers with the names of the companies. Now, this plot is generated by a graph drawing algorithm that calculates the positional coordinates of the vertices. And what this algorithm tries to do is to spread out the vertices to make the plot more readable. But at the same time, it brings them closer together, the stronger the connection, between the vertices is. So what we can see from the plot here is that this red group appears to be kind of like a core of strongly interconnected companies. And the blue group is more of less connected companies at the periphery. Now, I also try running the algorithm with different numbers of groups. Here I set 3 giver groups and 2 receiver groups. You can see that the receiver partition over the rows does not appear to be particularly interesting. And adding a third giver group also doesn't add much, it seems. It should be mentioned that I also use the likelihood-based criterion for choosing the numbers of groups, and it suggests 2 giver groups and 1 receiver group consistent with this figure I showed you first. Now, I also do like an out-of-sample forecast validation exercise just to explore if these groups that we find can be useful for forecasting. So I do the simplest possible thing here, and I estimate the VER1 where I only use the red group variables on the right-hand side. So I throw out the blue group variables as regressors. I then forecast all the variables in the panel one step ahead, over a 3-year period and calculate the mean squared error. Now, the table here shows the reduction, the percentage reduction in mean squared error that the red group VER has compared to the alternatives. So a positive number here means that the red group VER did better. Now, in the rows, we have the results by industries, but let's just focus on the overall picture. We can see that the red group VER does better than OLS, and it also does a bit better than the ridge, and it does roughly on par with the lasso. Now, it's important to emphasize here that the message of this slide is not that I have a new estimator that everybody should use. It's more of an experiment to explore if these groups can be useful for regularization and forecasting. And it does seem by these results that they could be useful. Now, just to summarize the paper, I have introduced a latent group detection method that I call the DISCO finder that uses the singular vectors of the sample autoregressive matrix to recover both the giver spillover group structures and the receiver spillover group structures for the series. I then introduce a flexible network-based VER model with an unknown group structure and show that the DISCO finder is consistent within this model in the sense that it recovers the unknown groups when n and t are large. And finally, I used the method to study group structure in the volatility spillovers amongst the constituents of the S&P 100. Now, since we're still a bit early, I wanted to use the remaining time just to give you a quick overview of what we did in the other papers in this series. Now, we already spoke about the VER blockbuster algorithm briefly before. Now, this algorithm is intended to find these kind of symmetric groups or blocks in the autoregressive matrix. And the intention earlier was not to say that this is a bad method, even if I know it may have sounded a bit negative. The point was more that this is a method that does a particular thing under certain assumptions. And outside of that, it might not be the appropriate method. So I just wanted to quickly show you the algorithm along with an application we had in the paper. Now, the VER blockbuster is very similar to the DISCO finder. The key difference is in the second step, where we symmetrize the sample autoregressive matrix by adding its transpose to it. And then you have a symmetric matrix, you find the correct eigenvectors, you row normalize them, and you apply k-means. Now, we use this to study clustering in Twitter topics around the 2016 presidential election in the US. The data set we had around 400,000 tweets taking place in a 26-hour period around the election day, the 8th of November. And the tweets were included based on having either of these two hashtags that you can see on the slide. Now, this data set comes from the Harvard Dataverse. It's not something we collected ourselves. But what we do with it is we focus on word counts within 30-second intervals. So we begin by looking at the top 50 words by frequency over the entire data set. And we do this because, as you can imagine, with Twitter data, there is a lot of crap. There's a lot of bullshit words and misspellings and so on. So we focus only on the top 50 words by frequency over the entire data set. And then we take 30-second intervals. And within each 30-second interval, we pull together all the tweets. And we just do word counts over these top 50 words within each 30-second interval. So in the end, we have 50 series, which are the word counts within each 30-second interval for these top 50 words. And we have around 3,000 observations over time, which are the 30-second intervals. Now here you can see a word cloud of the top 300 words, just to get a feeling for what's going on. The larger the word, the more often it appeared. You can see the dataset was dominated by words like Clinton and Trump, America, vote, president, and so on. And here you can see the results when we cluster into 4 groups. Now, if we first look at the yellow group, it contains words like USA, US, and Yemen, which is countries. In the green group, we have politically neutral words that are related to the election, like polls, voting, vote, voted, but also admittedly, I'm with her, which was a popular hashtag for Hillary supporters. Then in the blue group, we have Clinton, Hillary, Hillary Clinton. And in the red group, we have Donald, America, Trump, President, American, and so on. Now, we also tried doing the same thing over the top 100 words. And here you can see the results for that. Now, the yellow group is as before, in addition to words like US, Saudi, and war. So it does have some kind of a theme of maybe international relations or something like that. The green group is as before, in addition to the words like ballot. Blue group is again Hillary and Clinton and so on, along with CNN. And then in the red group, we again have Trump and country, America, and so on, in addition to words like God and MAGA. Now, I want to quickly also show you the first paper in the series, which was the blockbuster algorithm. Here, we used a similar method to find blocks in the sample covariance matrix. Here, contrary to what we've been doing, the focus was on grouping by contemporaneous dependence, whereas in the other papers, we were focused on this intertemporal dependence in the autoregression matrix. And it turns out that we can actually interpret the groups we find here in terms of partial correlations. And this is because the inverse of the covariance matrix, which we call the concentration or precision matrix, is intimately related to the partial correlations of the panel. In particular, the ijth partial correlation is equal to the negative of the ijth element of the concentration matrix up to a scaling with its diagonal entries. Now, the blockbuster algorithm is, again, very similar to what we've seen before. Estimate the sample covariance matrix, take the appropriate eigenvectors, row normalize them, and run k-means. I want to show you 2 applications of this algorithm. The first one, we use a data set from Hamilton and Ovian. They have data, quarterly data on payroll employment growth for the states of the US. So we have 48 series and around 200 observations. What they do is they try to cluster the data into 3 groups based on a Bayesian Markov switching model. And I'm going to begin by showing you their results in this figure here. So they report cluster membership probabilities for each of the groups. And you can see here, or maybe not see here, that the darkest color here means over a 75% probability of belonging to the cluster. So the first group appears to contain some of the states in the middle of the US, the oil-producing states. And in the third cluster, we have some of the East Coast, along with maybe California and Arizona. And the second group is maybe a bit harder to interpret. It could be maybe some residual group. But we also run our algorithm on the data and ask it to find 3 groups. And here you can see the results it comes up with. Now, our red group is quite similar to their first group. Of course, it contains much more, but it contains the oil-producing states in addition to many other things. The green group is roughly comparable to their third group, the East Coast, along with California and Arizona. And then the blue group is the manufacturing Midwest. Now, it's important to emphasize here that, of course, these results are not directly comparable. We use very different methods, and they also use some exogenous covariates that we did not make use of. And of course, they also report cluster membership probabilities, whereas we just give point estimates. Now here you can see the correlation matrix of the data after ordering it by the groups. So you can see the groups are characterized by high correlation and weaker correlation between them. As a final thing, I want to show you our other application from that paper, where we had yearly growth rates of gross regional product for the NUTS1 regions of Europe. So here, each country is partitioned into several regions, and we have data on the regional level. However, we only have 13 years of data for, and this is on a yearly basis. So we have very few time series observations, only 13 of them, and around 100 regions. So we should, of course, interpret these results with a great deal of caution because it's a very small sample. But nevertheless, I think the results are very cool. You see, the algorithm is not given any geographical information here. It's only given the regional product for each region. And it comes remarkably close to finding country borders. So you can see here, for example, the green group is the UK, blue is kind of Poland, cyan is Germany, pink is Italy, France is red, and Spain and Portugal are yellow. Now, at the time we did this application, I was living in Barcelona in the region of Catalonia in Spain. And during this time, there were strong calls for independence of Catalonia from the rest of Spain. And this figure was quite popular with some of my colleagues because, as you can see, the region of Catalonia here is put with France instead of the rest of Spain. That's all I have today. Thank you very much for listening. And of course, thank you very much to the organizers for inviting me and organizing this.
Wonderful. Thanks, Stefán. Wonderful talk. Let me stop the recording.